now is the part in which I will actually talk about non-holonomic constraints, but we'll start by addressing actually one of the problems that we have with the walking robots, which is impacts. So inequality constraints are basically a type of constraints that you have in your system, in which your system is allowed to move in the interior of some open submanifold, but then you have a boundary submanifold that your system cannot surpass. So when your system gets to the boundary, you have some kind of impact. And an inequality constraint is basically a boundary on the open submanifolds of where your system lives. So that is basically for us an inequality constraint. But of course, examples of inequality constraints are systems with impacts, like the basketball when it hits the ground. Another example is our walking robot. Every time his foot hits the ground is also an impact condition. So this is also a system with some inequality constraints. So mathematically, for us, an inequality constraint is exactly a manifold with boundary that is defined by some expression of this type, where G is a smooth function. And I've used the notation, we'll denote sometimes the del of C, partial of C, will be the boundary of these constants of this set. So this set of points where the function G is equal to 0. And of course, for these systems, when they are in the interior of this kind of manifolds, then they are regular systems without constraints. In this case, where I've picked a Lagrangian function, they satisfy all the Lagrangian equations. But then, when the system hits the boundary of our set, there is an impact, and we must be able to predict where the system will be immediately after the impact. And so there are several ways to derive these impact conditions. The way that we'll use today is basically a generalization of a paper by Jerry Marsden, in which they deal with these kind of impacts. So the impact conditions basically give you energy conservation. That is the most basic one. Not all impacts conserve energy. These are elastic impacts. And the first condition basically tells you how momentum changes after the impact. So the first condition tells you that the difference between the momentums must belong to the normal subspace at the point at the impact point. So basically, the momentum is conserved in directions tangent to the boundary, and in such a way the difference must belong to the normal space, or orthogonal space, if you want to think it that way, in Euclidean space. So our paper deals with systems with non-holonomic constraints besides having inequality constraints. So these systems appear, for instance, in billiard systems, in which we have a rolling ball in a table. So this is a non-holonomic constraint, as I've shown you in the last presentation, and it has inequality constraints. Every time it hits the sides of the table, you have an impact. So, I can jump this part. I can skip this. It's the same slide as before. And now I just wanted to show you how the equations of non-holonomic systems with linear constraints is deduced from Lagrange-D'Alembert principle. So these equations are obtained from an action functional, the same one as in unconstrained mechanics, just the integral of the Lagrangian over the motions. And we pick variations of curves vanishing at the extreme points, and for which the variations must belong to the distribution. proceeding this way, eventually end up with Lagrange-D'Alembert equations, which give you the equations of motion for systems with linear non-holonomic constraints. Now, and what happens if we have an inequality constraint? How should this principle be changed? So, when you deal with inequality constraints, the trick in Marsden paper for unconstrained mechanics is expanding your space of curves where the functional is defined from a space just consisting of curves from R to the configuration manifold and adding the instance of impact. So the times of impact, the instance of time where an impact occurs. So that is the same procedure that we've chosen to follow in our GSI paper. So we've picked the action functional. We have expanded the space of curves in which the action functional is defined. Now the space of curves does not only consist of curves C to the configuration manifold, but also by instance of time where an impact occurs. And the variational principle states that the differential of our functional should annihilate variations that vanish at the endpoints, and for which, with variations belonging to D. And in that way, well, we work the equations. The differential of the action splits in 3 different integrals. 2 of them where no impact occurs, and well, a third term which is the term where an impact does occur. And so on the time intervals, which are the one from 0 to Ti and the other one from Ti to H where no impact occurs, Lagrange-D'Alembert equations will be satisfied. The only problem is what happens at the impact times. And so using the condition that the curve, the point must belong to the boundary of our inequality constraint at the moment of impact, we are able to get the impact equations, which basically tell you that that the velocity after impact must be in the distribution. That is the third equation. The second one gives you energy conservation. So then again, this is an elastic impact. Not all impacts satisfy these equations. And the momentum equation tells you that the difference in momentum is either on the normal space or in the annihilator of the distribution. So this is what you get, and this is actually corroborated by other methods that existing in the literature to obtain these impact equations, namely those from Weierstrass, Ederman conditions. I don't recall the name of the second one, but yeah, we can discuss it later if you are interested. So the first part of our paper is the derivation of the impact equations. The second part is proposing a variational pseudo-variational integrator for these kinds of systems. So a variational integrator is basically, if you don't know, is a paradigm for numerical integrations of dynamical systems, in which instead of discretizing the equations of motion, you instead discretize the Lagrangian function and the configuration and the tangent bundle, actually the phase space. And from that discretization, you will eventually get a difference equations instead of a differential equation, which will be your numerical scheme. So proceeding according to this framework, we first define a discrete Lagrangian. The space where a discrete Lagrangian is defined is Q times Q. Q times Q, in some way you can think that it replaces the tangent bundle. and you can intuitively think that the velocity is replaced by the difference of 2 points, and that is basically the reason why you get q times q. And then r is the time step, because if you want to get approximate velocity from 2 points, you make the difference between 2 points and then divide it by a time step. Then we must discretize the distribution. The discretization is just a submanifold of q times q with the same dimension as the distribution. And then we define the discrete action, which is a functional on a space not of curves, but in a space of sequences. This notation C sub d super n of q is just a space of sequences, n length sequences, of sequences containing actually n plus 1 points on q. In any case, we get a discrete function, and then what we do, we find critical points of the discrete action, and in unconstrained mechanics we eventually find what we call discrete Euler-Lagrange equations. In our case, we will find discrete Lagrange-D'Alembert equations because we have non-holonomic constraints. So that is basically the procedure adopted in here. This is the procedure without any inequality constraint at all, because then we must add inequality constraints. And how do we do this? So again, we expand the space where our discrete functional is defined to a space containing not only a sequence of points on q, but also impact times. And then we basically make the analogous computation to the one we did in the continuous part. So our space will now be not only a sequence of curves, but one of them will be on the boundary. I will consider that an impact occurs. So this q bar is some point in the sequence that hits the boundary of our inequality constraint. And then I will have a sequence of times that represent, well, that represent the times at which the continuous trajectory gets to q sub 0, q sub 1. So basically, q sub 0 approximates the trajectory at time 0, q sub 1 approximates the trajectory at time h, q sub I minus 1 approximates the continuous trajectory at I minus 1 times h, and then I have a t-bar. That is the time at which q bar hits the boundary of C. And this t-bar is not evenly spaced between I minus 1 times h and IH. It is actually some point in between, which is basically what we have here. So this is a parametrization of what q bar should be. And using all this notation, we are eventually able to split the discrete action into 4 different terms and work them all out separately. And some of them just give us discrete Lagrange-D'Alembert equations, and the other ones will give us impact equations. So let me see, I don't want to get lost. So the first two equations, the first two equations basically give us discrete Lagrange-D'Alembert equations, what happens away from the impact points. And then we have impact equations, 3 impact equations. Well, 1, 2, 3, more than 3, 4 impact equations. The first one is the momentum equation, how momentum changes. Then we have energy conservation. Then we have the condition that q bar belongs to the impact to the boundary of our set. And then we have, well, the discretization of our non-holonomic constraint. So this is the integrated. It is a very complex integrated, very difficult to implement. In any case, we were able to run it for short times, and we obtained, well, not so bad results. It's true that there is a jump in energy immediately after impact, but we still attribute it to numerical errors, since it's the scale is very small. but yeah, this is something that we must work out to understand how this integrator works in practice and understand its flaws, and that's it, basically. Thank you.
Thank you very much, Alexander. So, there are some comments or questions, please.
You are courageous because it's a tricky problem.
Yeah.
Do you know the book written by Michel Frémont? The title is simply Collisions. But unfortunately, I have the book in French. I don't know if it was translated to English.
I don't know the book, but
do you understand French? No.
Maybe I could understand.
So,
I can read it.
So I recommend you this work. Maybe there is a translation also. Also, there is important literature on numerical methods to solve problem of a great set of grains, rigid grains. Is discrete element method.
Yeah,
maybe you know.
The literature is very extensive about collision impacts. So actually this is just an approach to deriving the collision equations, and for us it was more about the approach using variational integration than about getting enhanced numerical methods. But still we want to study it to extend our study of these numerical methods to understand if it has some advantage comparing to existing methods.
By the way, there exists an integrator proposed by Jean-Jacques Moreau. He was an outstanding scientist in the convex analysis, but he worked also in numerical analysis, and he proposed a very interesting, in my opinion, integrator to face the problem of collisions.
Yeah. Thank you.
Thank you. More questions? Yes, I had two comments.
Okay.
One is that this type of constraints were called initially impulsive constraints, and then they were called unilateral constraints for obvious reasons. Then you use this inequality constraints, and now these are the hybrid systems. So this is the, and the second comment is the first time that I saw geometrical treatment of this kind of impulsive constraint was in a paper in 1919 by Ernesto Lacomba and Tuchiev in Journal of Physics A. So probably it's the first geometrical approach to this kind of problems. So thank you.
Okay, thank you.
Thanks again to the speaker.